Um, so this is ongoing work with Paola Giannini, and it's actually the follow-up of, it's a small follow-up on some joint work with Mariangela De Zani and Paola Giannini on using event structures as a semantic model for multi-party session types. And what we did in that work, so I will use MPST and ES as abbreviations in the rest of the talk. So what we did there was to pick a very simple multi-party session calculus where sessions are described as networks of sequential processes specified by sequential global types. And we give an event structure interpretation for both sessions and global types using two kinds of event structures called flow event structures and prime event structures. Don't worry if you don't know about them, I will introduce them. And our main result is that when a session is typable by a given type, then their associated event structures have isomorphic domains of configurations. They have isomorphic computations. Configuration is the name which is used for event structures to name computations. Can you hear me if I go this way? Because the
How is this streaming, but now it's...
okay, sorry.
You don't have to move.
Okay. I find it more comfortable to move around. Yes. And so we did this both for synchronous communication and for asynchronous communication. And the synchronous case is now published at the beginning of this year, while the asynchronous case is under submission, but you can find on arXiv a recent version, just submitted, a revised version submitted a couple of days ago. So this is just for a recap of what we did, and I will have, unfortunately, I know that some of you have been exposed already to this material, in particular some Oxford people there, and Simon, and maybe Peter as well. Actually, here I'm going to concentrate on the synchronous case, and I remember in Dagstuhl I presented the asynchronous one, so there will be some difference. So here we will concentrate on the synchronous case because that was chronologically the first we studied, and also because the paper was already published, so we thought it was better to rely on that. So, and what this talk will add with respect to the previous material, which I will recap, is some reflections on what this semantics is good for. So this was not only a natural question to ask in the very beginning, but it was also spurred by several remarks we had when we presented this work. I can remember Simon, for instance, or Nobuko, or some Ray as well. So they all sort of prompted us to explain why we were interested in such a semantics in the first place and what benefits we think we can draw from it. So indeed, we claim this is a denotational semantics for session calculi, so we expect it to provide some abstraction, for instance, and some new insights. And also, since we give semantics both to networks and to global types, can we establish a semantic counterpart for the syntactic well-formedness conditions on global types? And as regards the semantics for networks, can we identify some structural properties that are satisfied by the denoting event structures? And also, since event structure semantics has been since a long time, studied for various kind of process calculi. How does our semantic compare with these existing ones? And finally, could we go as far after identifying these structural properties? Could we go as far as completely characterizing the class of event structures that we obtain by interpreting networks and their global types? So these were the questions we were faced with. And as I said, here I will focus on the synchronous case, and I will just present you some very preliminary results and some conjectures. So, but first of all, I have to sort of set the background. So I'll start with a quick tour on event structures, and please, Antonio, control me because I always overflow. And this is, I mean, there is a lot of material here. I will try to be fast on the first part. So event structures are a canonical model for concurrency, which was introduced more than 40 years ago by Nielsen, Plotkin, and Winskell, and it was the subject of Glenn Winskell's thesis. And what is very appealing about this model is that it has a strong connection with both a particular class of Petri nets called occurrence nets and with a particular class of domains. Remember, those were the times where people were still looking for a denotational semantics for concurrency. So being close to Scott information domain was somehow a good starting point. So the simplest kind of event structures, the ones which were introduced in that seminal paper, are called prime event structures. They are essentially a set of events with two relations of them, a causality relation, which we represent by this arrow here, which is a partial order, and a conflict relation, and which is meant to say when an event must precede another one in any computation, and a conflict relation, which we represent by this squiggly line here, which is meant to say when two events are mutually exclusive. They can never happen together in any computation. And this conflict relation is assumed to be irreflexive, symmetric, and to satisfy this conflict heredity property, which says that if an event is in conflict with another one, and this E prime here causes an event E second, then E is also in conflict with E second. Namely, conflict is inherited by successors. And this property 3 here, the conjunction of irreflexivity and hereditariness of conflict, is quite powerful. It implies that the two relations of conflict and causality are disjoint, and that an event cannot have two conflicting causes. So that's quite easy to see, because if this E second here were this E, so if E and E prime were in both relations, then by conflict heredity, this E should be in conflict with itself, which is not possible since conflict is irreflexive. And similarly, if E and E prime were both causes of, did I step on? So we're not supposed to keep a slide for a long time. Okay, I will go faster now. So similarly, if this E, suppose E and E prime are both causes of E second, two conflicting causes, then this E will be both in the conflict and in the causality relation with E second, and we just said that they cannot be overlapping. So prime event structures are very simple, but they forbid conflicting causes, and they partition the relations on events. So the problem with prime event structures is that they are not flexible enough to give semantics to process calculi. And this is a very simple example in CCS. So if you have A prefixing C in parallel with C bar prefixing B, the way you would naturally interpret these with prime event structures would be, with event structures in general, would be to just create a new event, tau representing the communication, putting this event in conflict with both its components happening independently, and then this new event will just inherit the causality relation from its components. So you would like to end up with something like this, but as you can see immediately, we step outside the class of prime event structures here, because here we have two conflicting causes for the same event, and also these two events A and B shouldn't be considered to be in a global causality relation, because there is a configuration when when C bar happens here followed by B, and A happens at the other side, so there is no communication. So in this configuration where we have A, C bar, and B, A and B are independent. So there is no more a global causality relation. So the way people define a prime event structures semantic for CCS is to duplicate actually that event B, so that you keep the properties of of prime event structures, but as you see, this has a cost, because as soon as you have a communication, you have to duplicate everything that follows. It's not a natural semantics. So that's why Glyn Winskell himself immediately stepped to a more general class of event structures called stable event structures, which allow for conflicting causes, but which use a second order causality relation on events, which is called enabling. So which defines when a given set of events enables a specific event. So we lose this nice graphical representation we had here. That's why with Gérard Boutol, we introduced an alternative class of event structures, which is just a very slight generalization of prime event structures, so which is comprised between prime and stable event structures, and which remains, still preserves a first order causality relation on events, and therefore a graphical representation. So now, so we saw that this would be the semantics we would like to get, and in order to do that, we have to relax the conflict heredity property and replace the causality relation by an immediate causality relation, which is not transitive. So that's the very idea of flow event structures. So now the set of events has, again, a conflict relation, which is only required to be symmetric. It's not required to be irreflexive anymore, not required to be hereditary either. And the causality relation is now given by this flow relation, which is just immediate causality. So it's just irreflexive. It's not required to be transitive. And the new feature is that the conflict relation is not irreflexive, so we can have self-conflicts. And these we use to interpret CCS restriction. And now the parallel product on these flow event structures is just a natural one, as I was suggesting before, and it is a categorical product. At least it is a categorical product given a certain structural property which is satisfied by CCS interpretation. And now, so these event structures are already unfoldings. The events actually represent event occurrences. So if you have an infinite behavior, that will be represented by an infinite event structures. But they still have conflicts, so they are not executions yet. And the way, so there is an additional semantics defined on event structures, which is given by configurations, which are indeed a set of events that may have occurred at some stage of execution. So for prime event structures, configurations are very easy to define. They are a finite set of events which is downward closed. So if an event is in the configuration, then all its causes must be in the configuration, and which is conflict-free. All conflicts have been resolved. For flow event structures, the definition is slightly more involved, but not too much. So left downward closure is now required up to conflicts. Namely, if there is a cause of an event, if an event is in the set and there is a cause of the event which is not in the set, that's because there is already another cause of that event which is in the set and which is in conflict. And again, the set must be conflict-free, and also the transitive closure of the flow relation within the configuration must be cycle-free. There shouldn't be causality cycles in a configuration. So within configurations, we retrieve a partial order of causality. Okay, so, but we started a bit later. Let me grab something. And, okay, then the domain of configuration of event structure is the partially ordered sets of its configuration ordered by inclusion. And these domains have a particular structure. They are the so-called prime algebraic coherent domains, whose, and this is a result given in the original paper by Nilsson, Plotkin, and Winskell, that the prime element of this domain are in a one-to-one correspondence with the events of the event structure, if it's a prime event structure. So the prime elements of an information domain are those which add a piece of information to the domain, which cannot be expressed as the soup of two other elements. And this is a picture from the original paper, which sort of summarizes this. This is an occurrence net. This is an event structure, pictured upside down. And this is its domain of configuration. And the prime elements here are this one corresponding to E1, this one corresponding to E2, this one corresponding to E3, and this one corresponding to E4. So just because this is used afterwards. So our multi-party session calculus now is extremely simple. Processes are just internal choices of outputs or external choices of inputs. Everything is directed. This is the very basic first restrictive syntax for processes. And again, so this definition is co-inductive, and we assume regular co-induction. And processes may be viewed as trees whose internal nodes are decorated by actions, by p-bang or p-query, edges by labels, and leaves by zero. I say this because our events will be actually paths on these trees. And sessions are a parallel composition of located processes enclosed within a participant. And okay, the LTS is just the expected one. There is nothing, absolutely nothing new here. We write a communication like this. This is P that sends to Q the label lambda. And as you can notice, processes here are just like local types. They send pure labels. They don't, there is no value attached to labels. Okay, so our types should exclude classical deadlock where the participants have mismatching expectations. They should also exclude deadlock due to circular dependencies where the mutual expectations are matching, but there is a causality cycle. And we also want to exclude starvation, namely this kind of what we call a denying choice, where two participants, P and Q here, infinitely choose the second branch, and therefore this third participant here will never get a chance to do its communication with Q. So we want to exclude this as well. So our global types have the standard semantic of global types, where choice is between a fixed pair of participants, and again, this is co-inductive and so on. The LTS is also the expected one, so you can do a communication at the top level, but you can also do a communication under a choice if the communication is independent from the choice. Projection is just like the original projection, except that it's defined co-inductively, and therefore, so it requires for a choice every third participant to have the same behavior in all branches. But since it's defined co-inductively, it actually admits more sessions than the inductive definition. For instance, this type here is projectable, while it's not projectable with new definitions. So this type here means that P sends to Q either the label lambda 1 and then Q sends to R lambda, or P sends to Q lambda 2 and then it recurs. So, in fact, this type is projectable in our setting, but it will be excluded anyway because it's not bounded, and this boundedness is the second property which we require for well-formedness, because in order to prevent starvation. So well-formedness will be the sum of these two properties where, okay, I forgot to say what boundedness means. It means that, global type G is bounded if for each subtree G prime of G, the depth of the first occurrence of every participant is bounded over all the paths of these G primes. And this property is not satisfied by that type. The type system is also very much standard. Okay, I will not. And the properties it ensures are subject reduction, session fidelity, in quite a strong form. So this implies that the two LTSs are of a type and the type network are bisimilar. And also this property of progress, that if there is a component a participant whose process is not terminated, then eventually that participant will be able to do a move. Okay, so that was okay, so well, yeah, so the event structure semantics takes some time to explain. So I will just say that, let me just go quickly. Okay, just say that an event in the event structure of the network will be a pair of what we call located process events. So these are events of two processes P and Q run by participants P and Q. And as I said, here actually the event of a process is a path in its syntactic tree. So this pi here is actually the action whose occurrences we are specifying, and this Z, which preceded, it's the sequence of actions which the process must do before doing pi. And so our events will be, by construction, they will have to be dual, not only in their last actions, but also in the histories, in their sort of causal histories to reach these actions. So these are the events of a network event structure. And okay, I will spare you everything. I just want to show you that there is some confluence after conflict in these event structures. because, as I said, conflict is not hereditary anymore. And just by interpreting events syntactically, as I said, we reach situations where there is, the same event can have two conflicting histories, can have two conflicting sets of causes. You see, this is the communication between R and S at the end of the execution of this process here. So first P and Q have to choose one of the branches, and then P communicates with R, and then Q communicates with S, and finally R and S can communicate together. But by the time we arrive here, since here we retain only the local history in R, we have forgotten the initial choice between P and Q. So that's why we have this confluence. And instead, a global, an event in the event structure of of a global type is something different. It's based on traces. So it's, again, we take the syntactic tree of the global type, we take a path, and a path leading to a specific occurrence of a communication, and then we build the event from there by taking off from everything. So we take a path of this kind, which represents a specific occurrence of alpha, and then we take off from this path in the tree all the communications which are not causes of the last communication. So in the end, we get something of this kind. So actually, we start off with a sigma prime, which is a path in the global type tree, and after taking off all the unnecessary events, or all the unnecessary communication, we end up with something like this, which is an equivalent class because it's taken up a permutation of independent communications. Okay, so that's just to give you a flavor. And so this is a type that types the network for which I show you the flow event structure before. And now the event structure we obtain is different because it duplicates the final event. Why is that? Because it keeps the whole global history here. So you keep all the causes which transitively, all the communication which transitively cause the last one, including those which do not involve the participants of the final communication. So that's just to give you a flavor because, okay, and in the end, we proved that the configuration domains we obtained in both cases are isomorphic by just lifting the configurations to the level of networks and global types and exploiting our results of session fidelity and subject reduction. Anyhow, so this was what we did before, and now the question was, so what have you achieved? Why have you done that? I mean, all this work for. And we claim that we have gone a little bit further on replying to these three questions. So for this one, we can say something precise, and for these two here, we are halfway through. So this is about the abstraction, while we have to speak louder. So when we construct our events for networks, actually we get rid, I didn't show you all that, but we already, so the classical deadlock example I gave you in the beginning, where you have mismatching expectations from two participants, this one gives rise to the empty event structure, just because you cannot build such an event with dual histories and dual actions. And this one I didn't show you, so anyway, we also rule out events which are not causally well-founded. So we already do some sort of garbage elimination when we define the semantics, while the three-philosopher deadlock, the one due to a causality cycle, this one gives rise to three events, because these events are mutually dual, but and they are all well-founded, but the only configuration is empty. So there is no configuration where they can occur. So here we get more or less the same thing that we get with an LTS. There is no additional abstraction. And so maybe this question, so we partly abstract away from deadlock, so we just throw away these deadlock states. And is this good or not? Can it be viewed as a sanitization? Now, when it comes to the semantics for global types, so as expected, we turn the implicit concurrency into an explicit one, because concurrency is primitive in event structures. And our main result is that global types that type the same network give rise to identical event structures, prime event structures. And so this is a bit stronger than we expected. So we could expect that they would give rise to isomorphic event structures, but we get actually a stronger result. And that's because of the way, of the syntactic way we build events. And so I'll conclude with this. So we have some semantic counterparts for the well-formedness conditions on global types. Now I'm not going to bother you with the technical definition, just to tell you there is one. We haven't completely proved them, but we are halfway through. And so also we have a semantic counterpart for boundedness. And the conclusion is that, okay, we have given this event structure semantics for synchronous sessions types. For typable sessions, we have the equivalence of the two semantics. So this was our previous work with Mariangela. And here with Paola, we have some preliminary results on the benefits of our semantics. So this is the most related work. And I think there is also, since I see Franco here, I think there is also work by you and Ugo and on, you don't, maybe I'm wrong. So maybe it's this work, which is, but in both cases, it's for asynchronous communication. Okay, and then I leave you that.
Questions? Marco, please.
Just a quick question. Sorry, I missed
to be recorded, do you mind just wait?
Oh, sure. I think I missed the first parts. I'm sorry, I was in another talk. But so you mentioned this global types that they have the same event structure. Syntactically, what do they differ on? Maybe I missed this bit.
No, they have syntactically the same events. So if you have two well-formed global types that type the same network, they give rise to exactly the same event structure.
Yeah, but if I had to look at an example, what would be the difference between two equivalent global types? Are you, for instance, swapping interactions that are on different roles, or?
Yes. You swap interactions. So maybe, I don't know if you were here, you start with a path so you may have different global types where an action occurs in very different places. So you start with a path in one of them, then you prune all the communications which are not causes of the last one, and then you take it up to permutation equivalence. And since all that is specified syntactically, you end up with exactly the same syntactic expression for events.
Okay, I also have a question on your slide about the deadlock. You were saying that so you have empty configurations, but the
You mean the last slide?
Yeah,
yeah,
one
yeah,
of
yeah,
the
yeah.
last slides.
Okay.
But
Anyhow, it was this one. For this one,
can you reason on the other direction? So if you having empty configurations, is that bad, or there are multi-party processes that make sense and have empty configuration there, right? So you cannot use the approach as an algorithm to decide for deadlocks, right? So what do you provide actually?
by way of
Detecting.
a detecting algorithm. So if, yes, maybe we would need some additional information on the event structure to mark the states which somehow have no successors or ending states without being terminated states. Because at the moment we do the construction, we know this. So we could want to remember this. Look, this is a kind of bad sync event or something. We could, yeah, indeed, this is a bit brutal. You just take them away and forget about them. But a good thing would be that somehow once you have this event structure without the deadlocks, from that you can reconstruct a network which is sanitized somehow, which doesn't expose this.
So thank you all. And thank you, Ilaria, again for the talk.